Basic Nerve Conduction Studies, Lecture number 2. Motor Conduction Study. When an electric stimulation is applied to a peripheral nerve, as we know, an action potential is generated. This potential starts traveling in two directions, one proximally, whereas the other distally. It is the latter, the distally, which contracts the muscle innervated by the nerve and generates a muscle action potential. The EMG measuring system measures this muscle action potential by electrodes on a muscle, which is also called an evoked M wave. By changing the stimulation points, it is possible to differentiate whether an observed abnormality is regional or diffuse. It is also possible to determine whether the main cause of abnormality is demyelination or axon degeneration. The function of peripheral motor nerves can be objectively assessed by measuring this. This is a picture of motor conduction study of the median nerve. As we see, here is the recording at the abductor pollicis brevis muscle. Here, first stimulation site is at the wrist. The second stimulation site is at the elbow. The third is at axilla. The axilla is the proximal stimulation site, and wrist is the distal stimulation site. As we see, the waveform at the wrist and at the elbow becomes more wider, while at the axilla it is tortuous and not the wave is not clear in shape. This is called compound muscle action potential. The difference between the three sites, as we see, as we see, there is a clear difference in the latency between the three sites. The wrist is the shortest, and the elbow is higher, and the highest is at the axilla. And this means the difference in the distance between the stimulation and recording. Compound motor action potential. In the motor, as we said, we must stimulate at least at two sites. The first stimulation site has a distal latency and a duration and amplitude. The proximal has proximal latency and amplitude and a duration. This is the components of the motor. The first crossing the baseline and return is called a phase. This shape is like a turn. It is called turn. Each time the waveform changes its direction, it is called a turn. Here it's called a baseline crossing. The duration is calculated from the first crossing of the baseline to the positive and the return from the positive to the baseline. This is called duration. 5 important points in motor conduction studies. Point 1. Electrode attachment sites. Attach the recording electrodes as follows. The negative part of the recording electrode is attached on the center of the belly of the muscle. The positive, which is called reference electrode, on the tendon or bone nearby. If the electrode placement is incorrect, the correct waveform can't be measured. If correct, the waveform begins at the negative portion, rising waveform, when the electrodes are placed correctly. Point 2. Stimulation intensity. A supramaximal stimulation should be used if stimulation intensity is not higher enough. The correct latency can't be obtained. Point 3. Skin temperature. The skin should be maintained warm. The nerve conduction velocity depends on the skin temperature. Low temperature causes low conduction velocity. If the skin is cold, warm the whole area where the measurement is taking place. Point 4. Sensitivity and analysis time. The sensitivity and analysis time should be carefully selected. The factory default setting represents the most commonly used ones. For example, in some pathological cases, the waveform may have much longer latency outside of the default setting. Check and change the measurement settings if necessary. Point 5. AC interface filter, which is the alternating current interface filter. The alternating current interface filter should be avoided. It distorts the waveform significantly in the above mentioned potentials. Remove the cause of the alternating current interference instead. Latency. This term, we will hear it more and more. Latency means the time length from the stimulation onset point to the rising point of the waveform. It represents the conduction time of the nerve fiber, which has the highest conduction velocity. The skin temperature affects the conduction time. Care should be taken about the temperature at the time of the test, since low temperature causes low conduction velocity. In many cases, demyelinization may cause longer latency. Amplitude. Amplitude is the potential difference between the first negative peak of the waveform and baseline. Lower amplitude is the general symptom of axon degeneration. In some cases, the potential difference between the negative peak of the waveform and the positive peak of the waveform may be used as the amplitude. Motor conduction velocity. Motor conduction velocity can be calculated by dividing the difference in distance between the distal and the proximal stimulation points by the difference in latencies between the distal and the proximal waveforms. In many cases, demyelinization may cause lower motor nerve conduction velocity. Distal latency can't be calculated because it includes the neuromuscular junction, the whole distal latency, the neuromuscular junction delay. In order to estimate the approximate conduction time, the distal stimulation point should use the same length from the recording electrode for every examination. In this case, the obtained latency is called either distal latency or terminal latency. Duration. Duration is the time length from the rising point of the waveform to where the polarity of the waveform changes from negative to positive. In some cases, the time from the rising point to the ending point of the entire waveform may be used as the duration. Saltatory conduction. A nerve conduction study is performed to assess myelinated nerves. Myelinated nerves transmit excitation by a mechanism called saltatory conduction. A myelinated nerve consists of an axon and myelin sheaths. The sheaths are insulators. When a stimulus is applied, the sodium ion channel of the node of Ranvier underneath the stimulated area opens and an internal current flows. This is the excitatory process. The current advances in both directions along the long axis of the axon. The current exits from the adjacent node of Ranvier and returns to the excited area to form a local circuit. The extracellular flow of the current opens the sodium ion channel in the adjacent node of Ranvier to generate further excitation. This mechanism is referred to as saltatory conduction, which means to leap or to jump. Because excitation is transmitted by leaps over the myelin sheaths, the conduction velocity through the axon is much higher when the axon is surrounded by myelin sheaths. When myelin sheaths become detached in demyelinization, saltatory conduction is lost and the conduction velocity is reduced. Also, if the axon is degenerated, the current can't flow, thus inhibiting the propagation of excitation. Click the stem or the sweep button to see saltatory conduction demonstration. This is the saltatory conduction, and this is node of Ranvier. Here is the myelin sheath. Compound motor action potential or compound muscle action potential. There are several types of muscle action potentials evoked by electrical stimulation. These are shown in the next figure. Type 1 normal biphasic and large amplitude waveforms. Type 2 multiphasic and low amplitude waveforms, low amplitude wide waveforms. Number 3 biphasic but low amplitude waveforms. What causes these waveforms? What do these waveforms mean? It is important to understand the differences among these waveforms since this leads to better understanding of evoked electromyography. The typical pattern of compound muscle action potential. Here is the normal, high amplitude, biphasic, and normal duration muscle action potential. Here we see low amplitude and long duration and multi-phase action potential. Number 3 or type 3, here is a low amplitude with normal duration and biphase action potential. A nerve consists of many nerve fibers. Also, nerve fibers with different diameters have different thresholds to the electrical stimulation. If the stimulation intensity is too low, only some of the nerve fibers are excited, producing inaccurate compound muscle action potential waveforms. In order to make sure to excite all fibers, the nerve should be stimulated at 120% intensity, or what is called supramaximal stimulation, to the stimulation level which produces a response with the maximal amplitude. Supramaximal stimulation. A nerve consists of many nerve fibers, as we said. When the stimulation intensity is gradually increased, the amplitude of the compound muscle action potential also becomes gradually larger. The latency also changes. When the maximum amplitude is obtained, all nerves are excited, which is the maximum stimulation level. However, it may not be difficult to maintain all nerves excited at this stimulation level over many trials. In such cases, the stimulation intensity has to be further increased to the supramaximal stimulation level. Motor nerve conduction study evaluates the nerve fibers with the fastest conduction velocity. Here is the figure of the supramaximal stimulation. The first stimulation intensity, and here changing the intensity up till reaching supramaximal. Sensory nerve action potential. The shape of the sensory nerve action potential is different from the motor action potential, as we see. Here, this distance is the amplitude, and between the two crossing the baseline is the duration. This is the peak latency, and this is called onset latency. Sensory nerve action potential. When an electrical stimulation is applied to a peripheral sensory nerve, an action potential is generated. The EMG measuring system measures this sensory nerve action potential or snap with electrodes on the finger. In a natural condition, a sensory action potential which is generated in a sensory receptor is transmitted from the periphery to the center, in another word, orthodromic direction. On the other hand, there is a method which stimulates a nerve and record the response at a peripheral level. This method measured an evoked potential which is a product of the excitement propagation towards the periphery, so it is called the antidromic method. By changing the stimulation points, it is possible to differentiate whether an observed abnormality is regional or diffuse. The function of the peripheral sensory nerves can be objectively assessed by measuring sensory nerve conduction. Here, a sensory conduction study of the median nerve of the 3 points of stimulation, as we said before. This is the shape of the waveform, as we see, with a different latency. Thank you.